This is from your handout, section 2.4. First question is, what is the general empirical formula for an acyclic alkene with one double bond? We recall that for a regular alkane, the formula would be CnH2n plus 2. But with an alkene, two hydrogens have to be missing so that the molecule can form a double bond. And therefore, the formula would be reduced to simply 2n. Two of the hydrogens are gone. In the next question, they ask, what would be the formula, the general formula for a cycloalkene? Now, in the cycloalkene, not only have you removed two hydrogens to form a double bond, as compared to the regular butane molecule. Say we had drawn a butane molecule. There would be hydrogens over here, 3 hydrogens on the terminal end. So it would be C4H10. But to form the double bonds, you have to remove 2 hydrogens, form the double bond, and you have to remove these 2 hydrogens to link these 2 carbon atoms. So this is what it would look like. So it's missing 4 hydrogens as compared to butane, which has the formula CnH2n plus 2. So the formula for a cyclobutane, or butene, cyclobutene would be CnH2n minus 2. The next step, I just want to point out that because double bonds do not rotate, they're rigid in their conformation. So I drew 2-butene as an example. 2-butene can be frozen with one methyl group down and one up, or it can be frozen with both of them up. We normally call them trans when they're apart, and cis when they're on the same side. IUPAC nomenclature is a bit more efficient because it reduces that designation down to one letter. E is the same as trans, and Z is the same as cis. E stands for entgegen, which is the German word for apart. Z is the German word for zusammen, which means together. Think of somebody with a German accent saying together, and it'll help you remember what zusammen means. 3 molecules of industrial significance, 1,3-butadiene, and 2-methyl-1,3-butadiene, also known as isoprene. Isoprene is used to show how molecules of synthetic interest can be put together. A lot of naturally occurring products follow what's called the isoprene rule. They can be built up using isoprene units. There are 3 substituents that you should memorize the structure of. One is the vinyl group, the other one is the allyl group, and the last one is the propenyl group. One way to recall what they're like is the vinyl group looks like a little flag. The allyl group looks like a flag with an extra elbow. And finally, the propenyl group looks like a vinyl group with a methyl group at the point where the double bond is. So, vinyl, allyl, propenyl. Here I've drawn a cyclohexane molecule with the 3 substituents 1 isopropenyl, 2 allyl, 3 vinyl cyclohexene. The next part of our assignment was 2-5, where we had to draw the molecule based on the name. The first name we had to use was 2,4,4-trimethyl-2-pentene. So the first thing we did is we draw a pentane. So I drew the pentane skeleton, and then I realized that the second position there was a double bond, so I drew the double bond at the second position. And then there are 3 methyl groups, 1 at the second position and 2 at the 4th position. So we get 2,4,4-trimethyl-2-pentene. There is no cis-trans isomerism on this molecule because there's 2 methyl groups attached to the end of that double bond. So whether you flip them or not, you get the same molecule. 1,5-hexadiene, you draw the hexane skeleton, and then you put the double bond at the 1st position and the 5th position. Again, no cis-trans isomerism because they end in H on both sides. So if you flip it over, it doesn't change the molecule in any way. Example C is 3-ethyl-1-hexene. Draw the hexane skeleton. Put the double bond at the 1st position, and at the 3rd position you have an ethyl group. D is 2-methyl-1-butene. Draw the butane skeleton. Draw the double bond at the 1st position, and at the 2nd position you have a methyl group. 1,2-dimethyl cyclobutene, draw a cyclobutane. put a double bond. Wherever you put the double bond becomes the first position, and that allows you then to put in the 2 methyl groups. So it's 1,2-dimethyl cyclobutene. Lastly, we have 2,4-dimethyl, 4-ethyl, 1-heptene. Draw the heptane skeleton. At the first position, you have a double bond. The 2,4-dimethyl appears here. Notice how I alphabetized with D first, and finally 4-ethyl at the 4th position. I added these 2 molecules for fun because they look like jumping figures. The first one is possessing an allele group at the 2nd and 3rd position. There's an isobutyl group at the 1st and 4th, and a cyclopropyl at the 5th. So we would name it 1,2-diallele, 3,5-diisopropyl, 4-cyclopropyl, cyclohexane. Sorry, I'm naming, I looked at the wrong one. I named this one. This one is called 2,3-diallele, 1,4-diisobutyl. These are the diisobutyl groups. These are the allele groups. There's 2 of them, so diallele. This is 5-cyclopropyl, and then the 2 the 2 alkenes, make it called a diene, and they occur at the 1st and 4th position, so we call it 1,4-cyclopentadiene. This one is named 1,2-diallele. Here are the allele groups. 3,5-diisopropyl. These are the diisopropyls with 3 carbons there. And 4-cyclopropyl, 4th position, cyclohexane. I named these 1 and 2 because the double bond, because these are all 3 carbon containing. I reasoned that the ones with the double bonds have a higher priority, so I put them at the 1st and 2nd position. And this molecule, there are 4 carbons in the diisobutyl, so I reasoned to put them here, put number 1 here because 4 carbons is higher priority than 3 carbons.